we're going to now take those atomic orbitals, the s and the p, and we're going to hybridize them. And the reason we're going to hybridize them is because of an observation that we can make on the shapes of molecules. And that observation is summed up by valence shell electron pair repulsion theory. And valence shell electron pair repulsion theory just simply states that electrons around a central atom try to get as far away from each other as possible. And that makes sense intuitively, right? You know that electrons are negatively charged, and you know that the same charges repel, like charges repel. So if you have two negative charges that are tied to this central point, right, as far as they can get away from each other, they're going to. And if you have two electrons or two negative charges around a central point, the farthest they can get away from each other around that central point is 180 degrees. So here I'm using my fingers to represent those two electrons or those two negative charges around that central point. They're tied to that central point. No matter what you do, the farthest you can get them away from each other is 180 degrees. So CO2 is that example. CO2 is the example where there are two groups of electrons, one here and one here, around a central carbon atom. Valence shell electron pair repulsion says the shape of a CO2 molecule is going to be determined by that desire to repel each other as much as possible, or that need to get 180 degrees away from each other. So valence shell electron pair repulsion theory is going to dictate some of the shape of our molecules. And in order to account for this, we're going to have to use hybrid molecular orbitals or hybrid atomic orbitals in order to describe how these shapes occur. And the reason why is because if you look at the geometries of s and p orbitals, they don't line up with valence shell electron pair repulsion theory. So we make these hybrid orbitals that do line up with valence shell electron pair repulsion theory, and then suddenly we get a picture that makes sense. So let's jump right into it, and we'll take a look at it. Keep in mind, valence shell electron pair repulsion theory just says you take your groups of electrons and you just try to keep them away from each other as far as possible. Alright, so let's do some orbital hybridization. This will make sense once we get to valence shell electron pair repulsion theory with some actual molecules. Alright, so first I have this orbital diagram, or this energy diagram, with my orbitals put onto it, where I have the first two shells of orbitals, or first two shells of electrons around an atom. The 1s is full, and the 1s is just a sphere around the center of the atom, or around the nucleus. We're going to ignore that. We care about the number 2 shell. 2s and 2p. Those are the electrons that we care about. And if this is a carbon, there should be 4 electrons in those shells. And I filled up my orbital diagram with my electrons using the Aufbau principle, lowest first, right? And then the ones that are in the p orbitals, which are degenerate orbitals, I put as spin parallel. So if we're going to do this thing where we pair up these electrons to give carbon 4 bonds, if you notice, as drawn, right, with my 2s and my 3 2p orbitals, the 2s is happy, right? So here's my carbon, right, and it's got a lone pair in the 2s orbital, and there's a 2p x orbital, a 2p y orbital, and a 2p z orbital, right? And there's one electron in 2 of the p orbitals, and one of the p orbitals is completely empty. That doesn't give me 4 places to bond to a carbon. That doesn't give me a carbon that can have 4 bonds. These two are already paired. They're not going to pair up and bond. These two can pair up and bond. There's 2 bonds. And then I have nothing here, so there's nothing to pair up and bond there. So if I were to use this orbital picture that we already have, I would not come up with a carbon with 4 bonds. I'd come up with a carbon with 2 bonds, a lone pair, and an empty p orbital. Remember, bonds are shared pairs of electrons, and if I have a complete orbital here, I can't share those electrons because that orbital is already full, and here's an empty orbital where there's no electron to share, Right? So in order to share all of these electrons, the first thing I'm going to do is what we call promotion. And so that's what I'm showing down here. I'm going to promote one of the s electrons into the empty p orbital. And that gives me 4 half-filled orbitals. And that's important because I need 4 half-filled orbitals so that I can share each one of those 4 electrons. If one orbital is fully filled or not filled at all, right, I can't share electrons with that orbital. So in order to have 4 bonds to a carbon, I need to do this promotion thing where I get myself to 4 half-filled orbitals so that each orbital can share an electron and accept an electron to form a bond, right, to get 4 bonds around carbon. Now, Aufbau principle says you fill up from your lowest energy orbital first, and then you go to your higher energy orbitals. And right now, I'm breaking Aufbau principle, right? I've got a half-filled s orbital, and that's lower in energy than these 3p orbitals. So that's an issue. Hybridization is how we take care of that. So instead of having a single s and 3p orbitals, I'm going to create 3 hybrid orbitals that are combinations. I'm going to create 4 hybrid orbitals that are combinations of that 1s and those 3p orbitals. Now, I'm going to name them sp3 orbitals. And the reason why I named them sp3 orbitals is because they came from a hybridization of 1s and 3p orbitals. So 1s and 3p orbitals. Right? And that's what sp3 stands for right here. sp3 means that these are hybrid orbitals that come from 1s and 3p orbitals. Technically, each one should be like 1/4 S1P3, right? That would be like the long way to write out this. Nobody does that, and that's not a convention or anything. We just call them sp3 orbitals. But there's 4 of them. They're composed of 4 orbitals, 1s and 3p orbitals, and they're all hybridized into these hybrid orbitals that are all the same shape. So we don't have one spherical s orbital and 3 p orbitals that each have 2 lobes of equal size or equal electron probability above and below the nucleus. We have 4 hybrid orbitals that have a little character of both. A little character of p, right? They've got 2 lobes, all of them, right? But also a little s character. One of the lobes is clearly bigger, right? It has a clearly bigger lobe, and that's where some of the s character is in this hybrid orbital. And there's some math that can merge these 2 shapes, right? So each one of these orbitals is like 3/4 p and 1/4 s, right? And there's some math that can hybridize these shapes and get us to these shapes that we see over here, these sp3 shapes. So once again, right, each sp3 orbital has 25% s character and 75% p character. But the key important part of this is because now with all 4 of those orbitals, they're all for the same shape. The electrons are equally distributed across the 4 orbitals. They're all the same distance from the nucleus as one another. The energies of these 4 orbitals are all equal. They're all degenerate, right? They're all the same energy, right? And that's what hybridization does for us. It gets us to 4 equal energy orbitals. We don't have 1s and 3p's with different energy levels. We have 4 equal energy orbitals. And now this works with the Aufbau principle. Now, instead of having a half-filled s at lower energy, I have spin parallel 4 orbitals, all of the same energy. And that means that I have 4 half-filled orbitals that can participate in 4 bonds around that carbon. Now, all of a sudden, the shape of the orbitals around that carbon changes. When you had 3p orbitals, they were aligned 90 degrees from each other, right? Px, py, and pz. And now, when you have 4 degenerate sp3 orbitals, this is where valence shell electron pair repulsion theory comes into play. Now we have a central point. There are 4 groups of electrons, 4 regions of electron density around that central point. And if you take those 4 regions of electron density and you spread them out as far away from each other as possible, you get a degree angle of 109.5 degrees between each one of those electron groups. And this is basically a tetrahedron. So this is a ball and stick model, right? And this kind of shows it, right? This kind of shows, right, that angle between the 2 groups of electron density in those 2 different sp3 hybridized orbitals is 109.5. Now, it's 109.5 because you're in 3-dimensional space. If you were in 2-dimensional paper, right, the farthest you could get 4 groups away from each other would be 90 degrees. But we're not in 2-dimensional paper, we're in 3-dimensional space. So now, if I push one of these groups sort of back, right, and I can tweak all of these groups just a little bit, I can get just a little bit more space between the electrons by doing that, as opposed to just having 90 degrees. I can get all the way up to 109.5. And in general, we're going to see that any atom that is sp3 hybridized is going to have an angle between those electron groups and consequently between the bonds that it creates of about 109.5 degrees. Okay, we can do this again, except where we reserve 1 p orbital. So in the case where we need to make a double bond cannot be composed of 2 sigma bonds. The reason why is because sigma bonds are head-on orbital overlap, and you can't have 2 head-on orbital overlaps occurring in the same space at the same time, because that's electron density groups that want to be repelling each other, and if you put them into the same space at the same time, you just have a ton of electron density. They would push away from each other and your bond would break and nothing would happen. So in order to do that, we have to create what's called a pi bond, and a pi bond is side-by-side p orbital overlap. So here I have it represented down here, where one of the 2 bonds in a double bond is a sigma bond, head-on sp hybrid orbital overlap, but the other one is a pi bond, which is side-by-side p orbital overlap. So I have to reserve 2 p orbitals. I have to reserve 1 p orbital on each carbon in order to make that side-by-side p orbital overlap. And if I'm going to do that, I can't use all 3 of those p orbitals in making my hybrid orbitals. So anywhere you see a pi bond, you don't have sp3 hybrid orbitals on that carbon or that atom. You actually have what's called sp2 hybrid orbitals. So start with our promotion, right? Put 1 electron into that empty p orbital, but now you're just going to hybridize 1s and 2 p's because you have to reserve a p orbital for that side-by-side overlap, that pi bond. So the pi bond is the second type of covalent bond that we're going to talk about here. And, I just described it, but we're going to talk about it a lot more, don't worry. But it's composed of side-by-side p orbital overlap, so I have to reserve 1 p orbital out of the hybridization. That means that my hybrid orbitals are going to be composed of 1s and 2p orbitals. Therefore, my hybrid orbitals are going to be called sp2. 1s, 2p's, sp2. And I'm only going to have 3 of them. I started with 3 s and p orbitals that I'm hybridizing together. I end up with 3 sp hybrids, and in this case they're called sp2s as opposed to sp3s in the previous example. That leaves me with 1 p orbital that can participate in the pi bond. So in this case, right, if you look at one of the carbons involved, that carbon has 3 sigma bonds, 3 head-on overlaps formed by interaction with its 3 sp2 hybrid orbitals, and 1 pi bond, here it is, 1 pi bond formed by side-by-side overlap of its reserved p orbital. So a pi bond is composed of that side-by-side overlap of p orbitals, and in order to do that, you have to reserve a p orbital out of your hybridization. So carbons with double bonds, or any atom with double bonds, in this case it's a carbon, that carbon has to be sp2 hybridized because it's got 3 sigma bonds, 1, 2, 3, and 1 pi bond, and that's this guy right here. So 3 sigmas and 1 pi. Those sigmas are going to be the sp hybrid orbitals coming off of that carbon, and the pi is going to be the p orbital that was reserved. If you have a triple bond, triple bonds are composed of 2 pi bonds in orthogonal directions. So orthogonal just means 90 degrees apart. Now we're reserving 2 of those p orbitals that just naturally fall 90 degrees apart. Let's say that they're px and py. And then we're going to have 2 hybrid orbitals that make up the sigma bonds. So a triple bond is composed of 3 bonds, right? One is a sigma bond, and 2 are pi, so 2 pi bonds. So 1 sigma and 2 pi, and the 2 pi are composed of 2 p orbitals on each carbon. So those 2 p orbitals, right, this guy, right, remember p orbitals have lobes on both sides, and this guy, those 2 p orbitals have to be reserved from your hybridization. So your sp hybrids now can only draw on 1 s and 1 p orbital, therefore they're called sp bonds. The carbon's hybridization would be said to be sp hybridized. Those orbitals are sp hybrids, right? They have 50% s character and 50% p character. And those sp hybrids mean that here, right, your 2 sp hybrids are going to get as far away from each other as possible. You're going to have a 90 degree bond angle between the pi bonds and a 180 degree bond angle between the sp hybrids. So that angle is going to be 180. All right, I don't think I mentioned this on the last slide. In sp2 hybridized carbons, now you keep those 3 groups away from each other as far as possible, and you get a 120 degree bond angle. Here in sp hybrids, hybrid orbitals, you get a 180 degree bond angle by keeping those 2 groups as far away from each other as possible. So this is an sp hybridized carbon, right? Each one of these carbons is an sp hybridized carbon, sp, right? sp, because 2 p orbitals were reserved. So if I look at this carbon, there should be 1 s and 3 p orbitals. 2 p orbitals are reserved, right? 1 purple p orbital, 1 blue p orbital, and then I have 2 hybrid orbitals that are composed of the other s and the other p orbital that are left. This is a hybrid sp, and this is a hybrid sp, right? And that's shown by hybrid sp and hybrid sp. So this is an sp hybrid, this is an sp hybrid, and they're making the sigma bonds. So once again, for carbon-based compounds and in general, all the compounds in organic chemistry that we're going to talk about, sigma bonds are composed of head-on orbital overlap of sp hybrids typically. So your sigma bonds are sp hybrids, your pi bonds are side-by-side p overlap, and if you're determining the hybridization of a carbon, that's talking to you about how many s and p orbitals went into making the sp hybrids. So for these guys, right, these are sp hybridized carbons. On the last slide, they were sp2 hybridized carbons. On the previous slide, they were sp3 hybridized carbons. And we'll see a lot of practice with that.